Hello. Uh, we're in the second lesson on the Smith chart, and in this lesson, we'll discuss how to plot impedance on the Smith chart and actually how to interpret and the results and use the Smith chart on some problems. Okay. Here are the steps in plotting impedances in the Smith chart. Since Smith charts are in what is called the normalized form, with R is equal to 1 at the prime center. Users customize the Smith chart for specific applications by assigning a different value to the prime center. Okay. The first step is to normalize the given impedance by dividing it to the characteristic impedance. Then, find the normalized R on the chart along the prime center. So, R is somewhere on the prime center. Next is to find the reactance point. Okay. With the inductive reactance circles at the top and the capacitive reactance circles at the bottom. Lastly is to plot the point of intersection of this R and the reactance. Okay. Uh, when we are reading the values from a normalized Smith chart, we should convert them to standard impedance form by multiplying the resistance and reactance by a factor equal to the resistance of the prime center. Okay. So for example, given we have a given of load impedance 50 plus J50 ohms and the characteristic impedance of 50 ohms. We are to plot the load impedance, this load impedance in a Smith chart. So step 1, we have to normalize. So we divide the 50 plus J50 by 50, right? So the result will be 1 plus J1. So our R is 1 and our X is 1 as well. So next step is to find the normalized R on the chart. So we can see that on the chart, 1 is actually at the center point, and then we will have to find X, uh, which is 1, on the bottom part, or the upper part of the Smith chart. Okay. So in this slide, we have a zoom view, okay, of our prime center, and we have 1 at the middle, which is our normalized R. Okay. And then, since our X is a positive value, then at the top of the prime center, we can see all positive reactants in this area. Okay, so our X lies on this particular side of the circle. Okay, then next step, plot the point where they meet. So in this case, in this particular area. Okay, yeah. So let's discuss before we go to the standing wave ratio, return loss, and reflection coefficient. Let's discuss the scales at the outer perimeter of the Smith chart. As you can see here, we have 3 scales on that side, on that part of the Smith chart. First is the wavelength toward the generator, the wavelength toward the load, and the angle of reflection coefficient in degrees. Okay. So the scale labeled toward generator begins at the zero resistance. So zero resistance, this part, and zero reactance line. and moves clockwise around to the infinite resistance position. One half of a circular rotation is 90 degrees, and on the Smith chart scale, it represents 1/4 wavelength. So, one full rotation on the Smith chart is 1/2 wavelength. The transmission line patterns of voltage and current distributed along a line repeats every 1/2 wavelength. So, we can say that a one full rotation from the zero line is equivalent to a 1/2 wavelength. The scale labeled toward the load also begins at the zero reactance point, although it goes counterclockwise, okay, to complete one full rotation or 1/2 wavelength. The infinite resistance point is the 1/4 wavelength mark. The reflection coefficient, or the ratio of the reflected voltage to the incident voltage, has a range of 0 to 1, but it can also be expressed as an angle from 0 to 360, from 0 to 180 degrees, or from 0 to minus 180 degrees. The zero marker is at the infinite resistance point on the right hand of the resistance line, here. Okay? So now, going back to the standing wave ratio, the return loss, and the reflection coefficient. At the bottom of the Smith chart, we have these radially scaled parameters such as the standing wave ratio, the return loss, and the reflection coefficient. Okay? So the standing wave ratio of a transmission line plotted on the Smith chart is a circle, actually. If the load is resistive and is matched to the characteristic impedance of the line, the standing wave ratio is 1. This is plotted as a single point on the prime center of the Smith chart. So, at the center of the Smith chart, we have the standing wave ratio of 1, right? As you can see in the figure. However, the impedance line usually at the normalized value is 50 ohms. If the load is not perfectly matched to the prime impedance, standing waves will exist. So in this case, or in these cases, the standing wave ratio is represented by a circle whose center is the prime center. Linear scales printed at the bottom of the Smith chart are used to find the standing wave ratio, the return loss, and the reflection coefficient. For example, to use a linear SWR scale, we simply draw a line tangent to the standing wave ratio circle and perpendicular to the resistance line on the left side of the Smith chart. Make the line long enough that it intersects the SWR scale at the bottom of the chart. So in this particular example, we have the standing wave ratio equal to 2. So in this slide, we are going to solve an example to show how we can use Smith chart to solve radio frequency and transmission line problems. So as discussed, when the load does not match the characteristic impedance in a given application, the length of the line becomes a part of the total impedance seen by the generator. The Smith chart provides a way to find its impedance. Once the impedance is known, An impedance matching circuit can be added to compensate for the conditions and make the line uh, at 1 at and the standing wave ratio as close to 1 as possible. Example, the operating frequency for a 24 feet piece of RG58AU coaxial cable is 140 MHz. The load is resistive with a resistance of 93 ohms. What is the impedance seen by a transmitter? Particular illustration on the right. The operating frequency of a 24 feet piece of RG58AU coaxial cable is 140 MHz. The load is resistive with a resistance of 93 ohms. What is the impedance seen by a transmitter? The first step is to find the number of wavelengths represented by this 24 feet cable. So, a 140 megahertz signal has a signal wavelength of 7.02 feet. So that will be wavelength is equal to 984 divided by f. We got 7.02 feet. So remember that coaxial cable has a velocity factor that is less than 1 due to the slowdown of RF signals in the cable. The velocity factor for RG58AU is 0.66. Therefore, one wavelength of 140 MHz is actually 4.64 feet. The number of wavelength for this 24 feet piece. So we have 24 feet divided by 4.64 feet per wavelength. So therefore we have 5.17 wavelengths for this particular problem. So as we discussed earlier, the impedance variation of a line repeats every 1/2 wavelength. Therefore, if we have a full wavelength, we only need the decimal part. So since the impedance variation along a line repeats every 1/2 wavelength, we remove the 5. Hence, we will use in this particular problem 0.17 of a wavelength. Okay, so step number 2, we will normalize the Smith chart to the given characteristic impedance of the coaxial cable, right? So, which is 53.5 ohms as given by the RG58AU. Okay, so we can now compute for our standing wave ratio, and our standing wave ratio will be equal to our uh, normalized value R. Okay, remember in the first lesson that the standing wave ratio will be equal to R if the load is purely resistive but unequal to the characteristic impedance. Therefore, uh, we have the normalized characteristic impedance 93 divided by 53.5, which is 1.74. Okay, so where is it? 53.5 will be our prime center, which is located at the center point of the Smith chart, and then we will plot the 1.74 of this particular at this part and the 93 ohms load impedance. Okay, then uh, we will plot our standing wave ratio circle on this particular line. So next, to find the impedance at the transmitter end of the coaxial cable, we move along the line. Okay, so we shall move along the line 5.17 wavelengths. So remember that one full rotation around the Smith chart is 1/2 wavelength. And because the values repeat every 1/2 wavelength, the starting point at x, at this point, we shall go around in by 10 times, right? So after 10 complete revolutions, it will represent 5 wavelengths, which will bring us back to the original position. Okay. And then, we shall continue the clockwise rotation for the additional 0.17 of the wavelength. Then we shall stop there. We shall mark the point on the standing wave ratio circle uh, equal to 0.17 wavelength. Draw a line from the prime center to the location that represents 0.17 wavelength. The marking on the right hand side of point X is our 0.25 wavelength mark, as you can see here. So for ease of calculation, we shall add 0.17 in that 0.25. Therefore, we can use the reflection coefficient or the wavelength scales at the perimeter of the circle, so we can get the 0.17 wavelength. Okay, so we have 0.25 plus 0.17, that will be 0.42. So as you can see in this particular illustration, we started at 0.25 and added 0.17 of the wavelength and stopped at around 0.42. So in that case, we shall draw a line connecting our prime center and 0.42 mark on the perimeter. Okay. The point at which the line cuts our standing wave ratio circle is the impedance that the generator sees. I repeat, the point at which the line cuts the standing wave ratio circle is the impedance that the generator sees. Reading this value from the chart, we have R approximately equal to 0.68 and a capacitive reactance because the plot is below or at the bottom of our prime center. We have a capacitive reactance of 0.35. Therefore, the impedance that the generator sees at this point is 0.68 minus J 0.35. Now, to find the actual value of the impedance seen by the transmitter, we shall multiply the normalized impedance by the characteristic impedance. Okay, so that will be 53.5 times 0.68 minus J 0.35, which gives us 36.4 minus J 18.725 ohms of impedance seen by the transmitter. Okay, so another example. In many cases, the antenna or the load impedance is not known. If it's not matched to the line modifies this impedance so that the transmitter sees a different impedance. One way to find the overall impedance as well as the antenna or other load impedance is to measure the combined impedance of the load and the transmission line at the transmitter end. So how? Using an impedance bridge. Then, the Smith chart can be used to find the individual impedance values. So, let's have this example, a 50 feet RG11U foam dielectric coaxial cable with a characteristic impedance of 75 ohms and a velocity factor of 0.8 has an operating frequency of 72 megahertz. The load is an antenna whose actual impedance is unknown. A measurement at the transmitter end of the cable gives a complex impedance of 82 plus J43. What is the impedance of the antenna? So we know that one wavelength at 72 megahertz is um, 13.67 feet. Taking the velocity factor into account yields 10.93 feet, as we can see here. So our wavelength is 10.93 feet. So the length of 50 feet cable in wavelengths is 50 divided by 10.93 gives us 4.57. As before, it is the 0.57 wavelength value that is of practical use. Actually, we shall use the 0.07. First, the measured impedance is normalized and plotted. The prime center is 75 ohms. So Z is equal to 82 plus J43 divided by 75 is equal to 1.09 plus J 0.52, which is plotted on the Smith chart. The standing wave ratio circle is then plotted through this point from the prime center. A tangent line can be drawn from the standing wave ratio chart on the bottom, which is 1.67. Okay. Next, a line is drawn from the prime center to the normalized impedance point and through the wavelength plots on the perimeter of the graphs. It intersects the toward load scale at point X or 0.346 wavelength. Okay. So the plotted impedance is what is seen at the generator end. So it is necessary to move around the graph to the load in a counterclockwise direction to find the load impedance. We move we then move a distance equal to the length of the cable, which is 4.57 wavelengths. Okay, so that gives us 9 full rotations from this point, which represents 4.5. So we still have to rotate at least or at exactly 0.07 wavelengths more counterclockwise. It is to complete the length. This puts us at 0.346 plus 0.07, which is equal to 0.416 wavelength point. We then draw a line from this point back to the prime center. Okay, so the point at which the line intersects the standing wave ratio circle is the actual antenna impedance. So the value, the normalized value of this point, if we read the chart, is 0.72 plus J 0.33. Then multiplying it back to 75 ohms gives us the actual value of the antenna impedance. Z is equal to 54 plus 24.75. 54 plus J 24.75 ohms. Okay, so those are basic examples of on how we can use the Smith chart to identify or solve impedances of transmission lines. Okay. First, we solve uh, when we have an antenna that is not known. Then we also solve uh, when the load does not match the characteristic impedance. Okay, so in the succeeding or on the next lesson, we'll find out that we can match impedances using different elements. Okay, so we shall use the Smith chart uh, to complement impedance matching networks for transmission lines. With that, this is the end of the lesson. Thank you.